Good morning, everybody. In this talk, I would like to reflect on our studies funded generously by GOMRI over the last 10 years on the basin scale and near scale circulation in the Gulf of Mexico. As you all know, we had a problem of this sort where we had a oil leak, multi-phase gas and oil at the bottom of the ocean, which rose through the water column. And then when it came to the surface, or rather the interface between the two largest reservoirs, fluid reservoirs on Earth, atmosphere and the ocean, the situation gets very, very complicated. You have very complex ocean currents. You have waves, very, very thin interface. And then you have also the atmospheric circulation, including hurricanes. And then the problem that's of greatest socioeconomic interest is how and when the oil spill or if gets to land. This is where it makes a big impact. So we had a lot of observational and numerical studies on these problems, and I would like to describe some of the main results. First of all, I would like to say that we had to develop a number of instruments throughout the project. None of these instruments were really available at the beginning of the project, and I would like to thank GOMRI again for trusting us that we would actually make something, even though initially it was on paper. During the project it became reality, which is very different from a PowerPoint to reality. So we developed an instrument that's a biodegradable drifter in order to release these instruments, water following. A very large number of them, which is needed for data. We also recognized early in the project that the problem is not just the ocean, but we need to also, we can observe, since the oil spills are at the surface of the ocean, we can observe from aircraft. So we put a lot of instrumentation on aircraft, such as high resolution sea surface temperature, as well as other aerial platforms such as aerostat. We had a balloon that we pulled from a ship in the middle of the ocean that was looking at a bunch of drift carts simulating biodegradable oil, as well as drones which didn't need drift carts or any other thing to be spilled in the ocean, but rather get the current information or velocity information from waves. We also had similar instruments to those that we installed, of course, much more accurate and more comprehensive on a ship, a marine radar that could detect or measure the currents around the ship within a several nautical miles radius. So these were all developed through the project to be able to attain our objectives. And using this instrumentation, we could actually zoom in many, many times and focus on the same area. Instead of doing multiple experiments, we chose the method of having multiple instrumentation. So we actually overlaid a bunch of instruments and we could see actually closer and closer. For instance, on the left panel, upper panel, we see how the sea surface temperature looks from satellite. But this resolution is not adequate, so we released drifters in a smaller area that's shown in this blue box here. And then within that, we could embed, for instance, airplane measurements. Within that, we could embed marine radar measurements from the ship. And within that, we could actually put aerostat measurements. So this way, we could actually go 120 times, 120x on the same patch of the ocean. And that's one of our strategies. We also, for instance, said, what if, for instance, Deepwater Horizon event happened in the winter time? The winter measurements are difficult because the ocean is very, very, there are a lot of fronts passing every week or something like that. So we had one measurement exactly 2 years after Deepwater Horizon where we had drifters instead of oil, and comparing to Deepwater Horizon, we get similar results. And then we went there in the winter time, released 1,000 of our drifters, and then got completely different results in that you had let's say a tracer or oil reaching the Mexican shelf, not the coast, because it comes on the shelf within a few weeks. So yeah, seasonality is striking. That's what I wanted to emphasize, the effect of seasonality on dispersion. And we also developed a very nice air, sea, wave model. This is a fully coupled model by recognizing that you cannot just get away just by ocean modeling or wave modeling or atmospheric modeling. You need a fully coupled modeling. And this is a Shui Chan's model. It's a one of a kind at this moment where all components talk to each other. It's not the atmosphere driving the ocean. This is a waves, everything is integrated and fully coupled model. And this model was tested. It was one of our main tools during the experimentation that we used when we went out to sea. This model and the Navy coastal ocean model was running, NRL model was running in real time, helping us really what to do next and so on and so forth, as well as providing, the experiments provided data to these models to actually improve them. And here you see the seasonality. In 3 of our experiments, we get completely different results because the loop current location is quite different. And then you can use these outputs to say what would happen to a spill area, how much beaching would occur, how much oil could be transported out of Gulf of Mexico, depending on the year and so on and so forth. You can see a lot of variability there. So this is instructive. It's not the one solution. Depends on the year, depends on the season. Also, another big wake-up call for us was how much local data that we needed. For instance, there was an event, Hercules event, that happened while we were actually preparing for a cruise, and all of a sudden I received a call from Gomri, and a small Gomri team was assembled and sent to this area on the Louisiana shelf, and we released drifters, and drifters were essentially stretching southwards. And this behavior was not reproduced in any models because this area fell in between satellite tracks that are hundreds of kilometers apart. So it's not just because you have satellite data means that you know the currents in the ocean. You can have a situation where the spill area is in between satellite tracks, or sometimes the satellites are out for one reason or another. They break or something like that, so you may not get data. So the conclusion from that is you need local data, okay? You cannot just rely on satellite data all the time. Another use, and I think this is one of the biggest contributions we made, was that we contributed to NRL modeling also, as well as NASA instrumentation through our experiments, because models are developed, they have excellent tools, but they need local in-situ data to be tuned. And once you know the truth, then it's very easy to correct these models. But if you don't know the truth, the model is a box that generates a solution space. It's physically consistent, Newton's law, but it may not have the necessary accuracy, necessary detail, unless you know the real truth, physical truth. So our experimentation, these drifters generated, for instance, what this shows is it's actually how fast the oil spill grows as a function of its scale. So if the model resolves the scales of motion, then it actually predicts very well the spreading. But as we all know, models have limited resolution. This one is 3 kilometer resolution. So what this graph says is that you have a dispersion deficit in that if you don't know the scales, the model is off, let's say, by an order of magnitude, under predicts the initial spreading of the plume. Same with altimeter. Altimeters have also the same kind of resolution problem. This is a AVISO, which means you don't resolve scales less than 100 kilometers or something like that. So this is a comparison of how altimeter data versus reality showed the growth of the plume, and the AVISO data shows an order of magnitude slower growth initially. And this actually created excellent collaborations with NRL and JPL, and JPL ended up attending 2 of our cruises and developing sensors that they are still testing under their own funding. So this is moving forward very well. The other wake-up call was how important freshwater fronts are in the Gulf of Mexico, northern Gulf of Mexico coastline. I didn't know much about that, but one day when we were releasing our drifters, this is in Destin, Florida, we couldn't make sense of why our drifters are in these places until we got a SAR image, fine resolution synthetic aperture radar image, and we overlaid at the same time just to find out that all our drifters are along these fronts. And then actually I took a boat, drove there, and then I found out all our drifters along the front visibly. These fronts are 1 meter wide, 3 feet. It's stunning how sharp they are. And they also, in practice, they play a role. For instance, Taylor spill, this is Deepwater Horizon is the largest spill. Taylor spill is the longest spill, 14 years. And it was never quite appreciated because we found out by going there and making a numerical and experimental study that because of the Mississippi River outflow plume, part of the spill goes to the west, part of the spill goes to the east, part of the spill goes to the south, but none of the spill goes to the Mississippi area. And therefore it went kind of undetected in some ways for a long time. Here, the freshwater front location plays a very, very important role. And again, we use this in another paper. There are some papers cited here. It's in PowerPoint and the paper that I wrote for this event. The Deepwater Horizon spill area can also be explained to some extent using this Mississippi outflow location. This is an extreme event that we detected by releasing 200 or 300 drifters in an array. And this is like a high resolution camera. What's happening here is that if you put enough resolution there using more instrumentation, you see strange things happening. Here, our initial array was the size of a city, 30 kilometers by 30 kilometers, and it shrank down to the size of a room in a few days. So the area construction is 1 million times. And what this implies is all the material at the surface of the ocean is sucked down. And that has obvious implications for oil spills. And so it's like a bathtub, ocean sink, and other metaplastics, and so on and so forth, and three-dimensional motion in the ocean. We also were able to, I'm very proud of this part as well, we were also very, gained clarity about what the models are doing, because the latest trends in modeling is you increase the resolution of the modeling and therefore you get better results. And we found out this is not the case, because especially in data assimilating models, because part of the range of the models are constrained by data, and that's the realistic part that is particularly relevant to forecasting. And here, drifters actually are excellent tools to assimilate into models. With a few drifters, you can correct the model very, very fast and efficiently. But then as you increase the resolution of the model, you go finer and finer and finer resolution, you're not making the model better in some ways. You're just increasing the number of unknowns, okay? So the data density per the totality of the mesh points decreases. So you have more unconstrained degrees of freedom that can actually make it worse sometimes. So you have to be careful. Sometimes coarse resolution models can give you better forecast. And now you have a range where if you don't know the physics, still. So there is a clarity here and a lot of insight we can progress regarding future. And then I'm also very proud of our data density, which span 5 orders of magnitude. And using this, we were able to show that Richardson 1926 for third law. This is a very famous paper by Richardson in 1926, which he made, essentially came up with by looking at 6 or 7 plume observations from factory stacks in London. And this actually turns out to be very, very accurate in the ocean, spanning this huge scale range. It's stunning how good this simple law is and applicable. This is all our data from all the stuff that I showed, even from Arctic observations. And the only time this law doesn't work is when you have a hurricane. We had a hurricane, we found out there's a lot of scatter around that, so it messes things up, dispersion law. So dispersion as a function of scale. We also recognize that when we talk about surface of the ocean and the oil spills are at the surface of the ocean, much of it may be 1 inch of the ocean. Nobody measures 1 inch of the ocean. I mean, when we talk about surface of the ocean, we are talking about 10 meters. So what is this? What are the currents at the surface of the ocean within centimeters versus 10 meters? So again, using our array of instruments that we developed throughout this project, we were able to come close to 1 centimeter of the ocean current and essentially publish a paper on that to find out that the currents at 1 centimeter are 4 times faster than currents at 10 centimeters, where oceanographers thought of surface layer being 10 centimeters. So that's a big difference, important for not only oil, but also plastics and so on and so forth. And also we show in this paper, I'm running out of time now, that the surface dynamics, in particular waves, have a big impact on explaining how landfall occurs in oil spills. So to summarize, I would like to say that winds, waves, and ocean currents, I mean, maybe it's obvious, but they're all equally important. You cannot underestimate or ignore one of them. And the best way to go about this for forecasting purposes is to have a fully coupled model that combines it all, okay? But there are not too many of them. As I said, we are only aware of one of them. If not, we have to make sure we have a good representation of winds and waves in ocean models. That's to say that we don't have it at this point in time. The second thing is another simple statement is high resolution modeling really requires high resolution observations, okay? So just because your model is high resolution only means that you have more degrees of freedom, you can have more solutions, but that doesn't mean that these solutions, however physical, will represent what's going on in the ocean at that particular time. So better make sure that you have high resolution observations. And also what kind of observations? Local observations. I mean, you need to go on top of the oil spill and generate the data. These are obvious statements. And near surface, and that's really, really important. And one way that we found out that's very handy is these biodegradable drifters that you can drop from aircraft. We made a version that you can drop for aircraft. They are inexpensive and get the data through satellite network immediately in real time under all conditions, night, hurricanes, it doesn't matter. You can generate the data and they can be assimilated in numerical models. And I would like to, again, thank Gomri for very generous support of our project for 9 years. And that's the real end for me. It's been a pleasure. Thank you.